Hi students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we will be doing this chapter called as EMI. Now last lecture we had seen what is a transformer. Today let's see what are the different types of transformer. First, if I had a transformer this way, where you have less number of turns, this is my soft iron core and I have more number of turns on the secondary, right? This is my primary P1, P2 and this is my secondary S1, S2, right? Now, such a transformer is called as a step-up transformer. Right? What is a step-up transformer? It is a transformer in which the primary coils consist of thick insulated copper wire having small number of turns, and the secondary coil consists of thin insulated copper wire having large number of turns. Since it's a thin wire, it will have large resistance. The resistance of the primary is less, the resistance of the secondary is going to be more. The primary is either wound on the secondary or it is wound on two separate limbs of the soft iron core. Now, since the number of turns of secondary are more than the number of turns of primary, therefore it converts a low voltage high current into high voltage low current. Fine, let's write this down. The primary coil consists of thick insulated copper wire having small number of turns and the secondary coil is made up of thin insulated copper wire having large number of turns and large resistance, having large number of turns, large resistance and weight and large length. Right? Now, since the number of turns of the secondary are greater than the number of turns of primary, since the number of turns of secondary are greater than the number of turns of primary, the transformer converts low voltage high current to high voltage low current. Why low voltage to high voltage? Because we know that voltage is directly proportional to the number of turns. So as the number of turns are more, that is the reason why it converts low voltage into high voltage. That's the first type of transformer, which is called as a step-up transformer. Now you could have exactly the reverse configuration where I could have large number of turns in the primary and I could have few turns in the secondary. This is my primary P1, P2, this is my secondary S1, S2, right? Soft iron core in the center. This is called as a step down transformer. Now what is a step down transformer? It is, in this case you have exactly the reverse configuration. The primary coil consists of thin insulated conducting material wire having large number of turns and wound on a laminated soft iron core. Right? The secondary consists of the secondary coil consists of thick conducting wire having small number of turns as compared to primary. Now, since the number of turns in primary are greater than the number of turns in secondary, therefore the transformer converts low voltage it converts high voltage low current to low voltage high current. Right? So these are the two types of transformers. You can have a step down transformer and you can have a step up transformer. Next, let's see the working of a transformer. Now, the applied EMF, in the case of a transformer, you would have EMF that would be applied to the primary. Now, as it is an alternating EMF, guys, see this. I have EMF applied to the primary. As it is an alternating EMF, it will go on changing with time. As the EMF changes with time, it is going to induce a magnetic flux in the primary, right? And this magnetic flux which is induced in the primary will keep changing. Now, the magnetic flux of primary is linked with the magnetic flux of the secondary. Hence, you would have a changing magnetic flux in the secondary. Now, as the magnetic lines of force remain contained in the soft iron core, hence the field lines across the primary, all the field lines which are there across the primary get linked with the field with the turns of the secondary, right? So as a result, the magnetic flux in the two coils is directly proportional to the number of turns in the two coils. Fine. Let's see this. Let's write this down. An applied alternating EMF across the primary goes on changing with time. Therefore, the magnetic flux with the primary, the magnetic flux linked with the primary, linked up with the primary also keeps changing with time. Right? The changing magnetic flux of the primary is linked or gets linked with the secondary coil through the laminated core. Right? Now, as a result of this, alternating EMF is produced across the secondary. Alternating EMF is produced across secondary. Finally, get this in clear. Now, once you have an alternating EMF produced across the secondary, the laminated soft iron core practically couples the whole of magnetic flux. The laminated soft iron core practically couples whole of the magnetic flux whole of the magnetic flux produced in the primary with the secondary. Right? Now, as the magnetic field lines remain contained in the soft iron cores, as the magnetic field lines remain contained in the soft iron core, therefore, all the field lines across the primary get linked with each of the turn of the secondary. Therefore, all the field lines across the primary coil get linked with each of the turn of the secondary coil. Right? Therefore, we can say that the magnetic flux linked with the two coils is directly proportional to the number of turns. The magnetic flux linked with two coils is directly proportional to the number of turns. Right? Now once I know this, then I can say that let us assume that phi p and phi s is magnetic flux of primary and secondary. Therefore, we have just proved that magnetic flux in primary upon magnetic flux in secondary is equal to number of turns in primary upon number of turns in secondary, right? Where Np and Ns are the number of turns in primary and secondary. Ns are number of turns in primary and secondary. Right? Once you have this, then I can say, let us assume that phi be the flux in each turn. Let's assume that phi is the flux in each turn due to the current in the primary. Phi is the flux in each turn due to the current in the primary. Right? And let us also assume that EP is the voltage applied across primary, and small EP is the EMF induced in primary. Right? So in that case, I can say that the EMF induced in the primary is directly proportional to the number of turns in primary into the change in flux. The change in flux with time will give you the EMF induced by one turn. There are n number of turns, so the total EMF induced will be nothing but flux induced in one turn multiplied by the number of turns. Now since by Lenz's law the flux will oppose the source, therefore I am going to put this negative sign. The negative sign indicates that the EMF induced will be in the direction opposite to the voltage applied. Similarly, I can say that the EMF induced in the secondary is nothing but the flux induced in each coil of the secondary multiplied by the number of turns. Negative sign indicates that it is going to be the EMF induced will be in opposite direction. Right? Now, I can say that EMF induced in the primary is approximately equal to the voltage applied across primary, and EMF induced in the secondary is equal to the voltage applied across the secondary. Right? Therefore, I can say that if I substitute here, I can therefore say that the EMF induced in primary is the voltage applied across primary is Np d phi by dt. Similarly, the voltage received across secondary is going to be Ns d phi by dt. Right? Now, if I divide these two equations, in that case, EMF in primary upon EMF in secondary is going to be number of turns of primary upon number of turns in secondary, and this is called as T, where T indicates the turns ratio. Right? So the ratio of EMF in primary to secondary will be equal to the turns ratio, the number of turns in primary to the number of turns in secondary. Right? Where I can say that T is the turns ratio. Right? Once I know this, I can say from this relation can be obtained by using three assumptions. Or this relation has been obtained by using Pre-assumptions. 1. The primary resistance and the current is very small. And current is very small. That is the reason why the EMF induced in the primary is equal to the voltage applied across the primary. The same flux is linked up with primary and secondary. The same flux is linked with primary and secondary. Meaning that there is no loss of flux. Very little flux escapes the core and the entire flux produced in the primary goes into the secondary. Right? Now let us find out what is the power input. Now the power input to the primary. Power is nothing but EMF into current. So EMF in the primary into current in primary. Similarly, I can say that power output from the transformer is going to be EMF of secondary into current in secondary, where I can say that IP and IS are current in primary and secondary. Right? Once I have the power output, then I can say that if I assume the transformer to be 100% efficient, if the transformer is 100% efficient, if it is 100% efficient, meaning whatever is the power supplied to the input, the same power should be obtained at the output, right? If it is 100% efficient, then power input should be equal to power output. That means EP, IP should be equal to ES, IS. Therefore, I can say that EP upon ES is going to be nothing but IS upon IP, right? But we had just derived that EP upon ES is equal to NP upon NS. Therefore, I can say that EP upon ES is equal to IS upon IP is equal to NP upon NS. If I join the two equations, right? Hence, I can say that EMF in secondary is nothing but NP upon NS, no, NS upon NP into EP. That's how I come to know how much EMF will be produced in the secondary. It is nothing but the ratio of turns multiplied by the EMF applied to the primary. Similarly, current in secondary will be nothing but NP upon NS into IP. That will tell me how much current will be produced in the secondary. Right? Do we get this thing clear? Now, from this, it is very clear there are two things that you understand from this equation. One, if the secondary coil has greater number of turns, if number of turns in secondary are greater than the number of turns in primary, then the voltage is stepped up. Because see, it is NS upon NP. So obviously if NS is greater than NP, the answer for ES will be greater than that of EP, right? And for such a transformer, look at this. If NS is greater than NP, then the current is going to be reduced because it is NP upon NS. So I'll get an answer which will be less than 1. Since the answer is going to be less than 1, therefore the current in the secondary is going to be reduced and the current in secondary and the current in secondary will be less than the current in primary, right? Such a transformer is step-up transformer. So in a step-up transformer, the voltage is stepped up whereas the current is reduced. Fine, do we get this thing here? Right? Next, similarly, I can say that if number of turns in secondary is less than the number of turns in primary, right? Guys, in this equation, if number of turns in secondary is less than the number of turns in primary, that means this fraction will be less than 1, hence the secondary voltage will be less than the primary voltage, then I can say that the voltage is stepped down. And now see, Ns is less than Np, that means this fraction will be greater than 1. Since this fraction will be greater than 1, therefore Is will be greater than Ip. Is will be greater than Ip. Fine, do we get this thing here? Such a transformer is step down transformer. Now this whole equation was derived on the assumption that the transformer would work at 100% efficiency. Would it actually work at 100% efficiency? Now, what are the practical losses, right? What are the losses on a transformer? Next, let's see this. Third, let us see what are the losses in a transformer. First, flux leakage. Why would the transformer not work at 100% efficiency? These are the reasons. First, flux leakage. What did we say? We said that the magnetic flux passing through every turn of primary is linked with every turn of secondary, which may not be true because of improper design. There may be, or because of improper design or air gaps, some amount of flux may leak out. If some amount of flux is leaked out, then what will happen? The magnetic flux in each turn of primary will not be linked with magnetic flux of each turn of secondary. Hence, the EMF induced in secondary will not be equal to the number of turns because some amount of flux has leaked out, right? So I can say the first is flux leakage. The magnetic flux passing through every turn of primary may not be linked pass through every turn of secondary due to improper design. Right? Either it will be due to improper design of the core or due to air gaps. In the core. Right? How do I minimize this? This can be minimized, this particular effect can be minimized if I bind the primary and the secondary upon each other. Right? I can say this can be minimized by binding the primary and secondary each other. Instead of winding them on two separate limbs, wind them on the same limb, one upon the other, right? Second problem is loss due to heating. Right, some amount of power is going to be lost due to heating. Now, due to the resistance of the wire used for winding, some amount of heat is going to be produced in the wire. Heat, that is I square R, current is flowing, it has certain resistance, right? So therefore, some amount of power is going to be lost in the form of heat, especially in the case of high current, low voltage winding. This is more predominant. Now this effect can be minimized by using a thick wire, right? So I can say that second loss why the transformer would not work at 100% efficiency is due to the resistance of the wire, used for winding. Due to the resistance of wire used for winding, heat produced heat produces I square R, right? In the wire, heat produced in the wire results in power loss, right? I can say this can be minimized, or I can say in high current, low voltage windings, this can be minimized by using thick wire. This can be minimized by using a thick wire, right? That's the second kind of loss. Third kind of loss is loss due to eddy currents. Let's see the loss due to eddy currents. In case of alternating magnetic flux, we have alternating current. The alternating magnetic flux will induce eddy currents in the soft iron core, which will cause the core to heat up. Due to the changing magnetic flux, an eddy current is going to be produced in the soft iron core. Current, metal has some resistance. Current and resistance will produce heat, so some amount of power will get lost, right? In order to minimize this effect, you use a laminated core and increase the resistance of the core, which increases the resistance of the core and reduces the eddy current, right? So, alternating magnetic flux induces eddy currents in the soft iron core, which and cause the heating of the core. Right? I can say this effect can be minimized by using a laminated core. Effect can be minimized by using a laminated core. This effect can be minimized by using a laminated core, which increases the resistance of the core. And reduces eddy current. right? So these are the losses that will occur which will prevent the transformer from acting at 100% efficiency. How do I define the efficiency of a transformer? How do I define the efficiency of a transformer? Efficiency of a transformer is given by the formula power output to power input, right? I can say efficiency of transformer is equal to power output upon power input into 100 if you want to represent it in terms of percentage. Now power output is going to be nothing but ES into IS, voltage in secondary into current in secondary, power input is going to be EP into IP. Fine, do we get this thing clear? So that is going to be your formula for efficiency of a transformer. Now for an ideal transformer, power input is equal to power output, therefore efficiency is going to be equal to 1, right? But because of the losses, the actual transformer efficiency is less than 1, right? And by suitable design and proper precautions, we can get a transformer with say about 95 to 96% efficiency. Right? So that's your efficiency of a transformer. Next, where do we use transformers? Where do I use transformers? They are practically used everywhere. They are used, one, in transmission of electrical energy over long distances. Transmission of electrical energy over long distances. Right? Second, they are used to obtain large currents in electrical windings. Right? That is, your step-down transformers are used for obtaining large currents, which are then used for electrical welding. Large currents used for welding. Then you also use them in voltage regulators and stabilizers to stabilize power supply. Voltage regulators to stabilize power supply. Then they are used in induction furnace. They are used in induction furnace. Right? And small transformers are used. They have multiple applications, such as they are used for loudspeakers, radios, television, telephones. It is practically present in every electrical circuit. Right? So those are your applications of transformers. Fine, do we get this in clear? Right. we will stop this here for the day. Thank you very much.